this session will be chaired by Professor Rahul Misra from CARE, IIT Delhi. He has recently joined in IIT Delhi, and he also works in the area of spintronics. In fact, his talk will be also first talk in the next session. So Rahul Misra, you can take over, and I will be around to help you. But maybe you can introduce the first speaker, and then we can go ahead.
Okay, so thank you, Professor. So we will in this session we have 3 invited talk and 3 talks, I think, by students. So our first speaker is Dr. Prasanta Kumar Muduli. Dr. Prasanta Kumar Muduli is at present assistant professor in Department of Physics, IIT Madras, and he finished his PhD, obtained his PhD degree from Department of Physics, IIT Kanpur. After that, he has a wide experience as postdoctoral researcher from Leipzig University, Germany, University of Cambridge, University of Tokyo, and TU Dresden. At present in IIT Madras, he is looking at developing quantum technologies that exploit the topological bulk and surface electronic states for the recently discovered quantum materials. So the title of present talk by Dr. Professor Muduli is on non-local spin-ball devices to study spin-to charge conversion. So I think I'll pass over the presentation to Dr. Muduli. He can start. So I'll okay, we can see.
Okay, so the slides is visible now. Okay, so hello everyone. So my name is Prasanta Muduli. So thank you very much for the nice introduction. And so I would also like to thank the organizer for inviting me for this workshop. And yesterday was very educational, so I could listen to very exciting talks by many speakers. And yesterday's theme was mostly on spin dynamics. Today I will try to cover something slightly different aspect of spintronics. And basically, I'll try to show how you can use non-local spin-held devices to study spin charge conversion. And most of this work that I will present today was done at University of Tokyo when I was working with Professor Washichika Otani. Let me start the pointer. And at the time I was at the University of Tokyo and RIKEN jointly. And so this work, all the work that I'll present has been done there actually. So the outline of my presentation is like this. I will try to cover 4 different topics. So first I will try to introduce what is spin current and how you can use non-local spin-held devices to create and detect spin currents. And then I will try to give a brief overview of this area, what is going on in this area and what are the future things one can think and expect in this area of non-local spin-held devices. And then I will introduce a new experimental technique that is called the spin adjustment method. And this method one can use to study spin charge conversion. And then I will give 2 examples. Like one example is how you can use this kind of spin adjustment method to study spin charge conversion in bismuth oxide copper interface, which uses a Raspberry effect. And I will also give another example where you can use the same method to study spin Hall effect in wire semi-metal manganese 310. So let me start from this spin current. So as you know, the current is usually made of electrons, and electrons have a charge and spin. So accordingly, we can define 2 kinds of current. One is charge current, which is some of the spin current due to upspin and the downspin, and the spin current, which is the difference of the upspin minus the downspin current. So there are 3 different possibilities that is possible. One is like suppose you have equal number of spins, equal number of upspin and downspin electrons, and suppose they are moving towards the right. So in this scenario, what will happen is the total charge current is 0, non-zero, but total spin current is 0. So this is what usually happens in a non-magnetic materials where you don't have any spin current but only a charge current. But in a ferromagnet, what happens is that you have an unequal number of electrons. You have more upspin than the downspins. So whenever there is a charge current, suppose both the electrons are moving in this direction. So in this case, you can have a non-zero charge current, also a non-zero spin current. And this kind of current is called spin polarized current. But there is another interesting things that can happen in which you have equal number of upspin and downspins, but upspins are moving towards the right and the downspins are moving towards the left. So in this case, you have a charge current is 0, but there is a non-zero spin current. And this kind of current is called pure spin current. And this is very exciting for applications because in this, if you make devices using pure spin current, you can have reduced Joule heating and worsted fields. So since the spin current concept came to existence, there has been a lot of theoretical proposals. Some of the early theoretical proposals involved making a spin field effect transistor by Datta and Das in 1990s, where they proposed that you can create switch on and off spin current in a transistor device and make a transistor which will work on only based on spin currents. Also, there are devices that has been theoretically proposed in which you can pass spin current in your circuits and create a all spin logic device, and you can switch your magnets using spin currents and store memory and create logic devices. All these theoretical proposals has been partially realized experimentally, but there are a lot of challenges in this area, and I will try to address some of these challenges that we face in this topics. So let me introduce what is a non-local spin half device. So the non-local spin half device looks something like this one. This is a picture of a non-local spin half device. So this device was fabricated by me using 3 different steps of electron beam lithography. So in this device, you can see there is a nanowire of ferromagnet. You can see this blue line over here. These are 2 ferromagnetic nanowires, and this is bridged by this non-magnetic copper nanowire. So in this device, you can create a spin current, also detect spin current. Let me explain how you can do that. So suppose you apply electric voltage between this ferromagnet and copper. What will happen is that spin polarized currents will be injected into the copper. So due to which electrochemical potential of the copper will be split like this picture over here. And due to the splitting, we'll have a non-equilibrium spin accumulation just below this injector electrode. And this non-equilibrium spin accumulation will diffuse inside this copper. And diffusion process will create a current, which you can define like this, which is the gradient of the electrochemical potential along this x direction. So based on so this is the gradient of the electrochemical potential along this x direction. So you can also define a voltage, which is called spin voltage, which is the difference of this electrochemical potential divided by electronic charge. So since you have a charge and you have a current and a voltage, you can also define a resistance, and which is defined like this, which depends on the spin diffusion length and the resistivity of the metal and the spin polarization of the material and some area cross section of the nanowire. So in case of a copper, spin polarization is 0. So we have only depends on the spin diffusion length and resistivity and area. So the spin resistance is a very important quantity in spin circuits because similar to electrical circuits, suppose you have a spin current circuit, you must know the spin resistance to calculate how much spin current is flowing in which part of the device. So I will refer to spin resistance quite often in this talk. So in this device, what happens is that now you have created a spin current, how you can detect it. So you can detect it by putting a voltmeter at the other ferromagnetic electrode and the copper. So in this case, you will detect a voltage, and this voltage you will detect because in this end you apply voltage and you create a non-equilibrium spin accumulation. But the other end, there is a non-equilibrium spin accumulation. Due to the reverse process, it will produce a voltage, and this voltage we call it non-local voltage. Note that this is not the voltage is not due to the charge current, because charge current is only flowing in the circuit over here. So this you can also define resistance, which is basically normalized to your voltage. And so what happens is that when these 2 ferromagnets are parallel, you will get a positive resistance, non-local resistance. And when they are anti-parallel, you will get a negative non-local resistance. And the difference between these 2 resistance is called the spin signal. So this kind of devices can be used to measure the spin diffusion length of materials. So as you know, spin diffusion length is a characteristic length in which defines how far a spin current can travel inside a material. So that you can by intuitively guess that if you vary the injector and detector separation and measure how far you can measure the non-local voltage, that will kind of give you an intuitive idea how much is the spin diffusion length of material. So first, suppose your distance is d and you measure spin signal, it will look something like this one over here. Now if you increase the distance to slightly higher distance, then you will see that your spin signal will be reduced. So if you make many devices in which you increase vary the distance between injector and detector and plot the spin signal, you will see that it will decrease exponentially. And from the exponential fit, you can determine the spin diffusion length of copper. And for example, here I measured the spin diffusion length of copper at 10 Kelvin to be around 1100 nanometers, which is almost like 1 micron. So let me introduce how the non-local spin device has been evolved through time. So as we know, in spintronics, there are actually 5 steps. First step is to create a spin current. Then you have to inject spin current into different material. Then you have to transport it, and then you have to control during the transport. And at the end, you have to detect it. So the most difficult part was the injection. So the first experimental realization of a spin current injection into a metal was realized in 1985 by Johnson and Silsby, where they could inject spin current into a bulk piece of aluminum using a ferromagnetic electrodes. So they could make a non-local spin half device, and they found that when the two ferromagnets are parallel, they have a positive voltage, and when they are anti-parallel, they have a negative voltage. And this was the first non-local spin valve device that was fabricated. But people were not much interested in this thing because this measurement was done at a very low temperature, 27 Kelvin. So the first room temperature non-local spin valve device was made in the year 2001 in the Bart van Wijs group in Netherlands. They could measure non-local experiments using copper spin transport channel at room temperature, and they found the spin diffusion length in copper is around 350 nanometers. So after this, people were much more interested in this kind of devices. And there was another breakthrough experiment that happened in our group, in Otani group, where I was working in the year 2007. So we could show that for the first time at room temperature, we could measure spin Hall effect using non-local spin half devices. I will talk more detail about this and how you can do that in later slides in more detail. So after that, actually, after spin injection into metal, people could also inject spin current into semiconductors. And the first spin injection into semiconductor silicon at room temperature was realized by Soros Das in the year 2009. And after that, people were also trying to inject spin current into superconductors. And in the year 2013, there was a clear evidence of a spin current injection and transport by this group over here in Paris, France. And they could see that the spin current also can travel inside the superconductors. So with time, actually, there was a big revolution happened when graphene was discovered. People soon realized that graphene can be a very ideal material for spin transport. And so the first non-local spin half device was fabricated in the year 2007 in the Bart van Wijs group again. So they could show the spin transport at room temperature. And right now, the best record for spin diffusion length in CVD graphene is around 13.6 micrometers. In fact, one can observe spin signal up to 45 micrometers. So this gives a very lot of opportunity for this kind of devices for practical applications. For example, in spin charge conversion community, then the graphene spin transport is now the most favored material for non-local spin half device compared to previous generation copper and aluminiums. So this is one example where in the Felix Casanova group in Paris, in Spain, they could measure spin Hall effect in platinum at room temperature using graphene spin transport channel. And in the same group, they also use 2D materials, for example, MOS2 to study spin Hall effect, interface effects. And also people are now using this kind of devices to study spin charge conversion in quantum materials, for example, while semi-metal in tungsten telluride. And this result is from Soros Das group in Chalmers. So this field is growing very fast, and so let me explain how you can use the spin resorption method to study spin charge conversion in much more detail in the next couple of slides. So before that, let me give a very brief overview of what is spin Hall effect, because there might be some students around here who are new to this community. So let me spend one slide on spin Hall effect. So in spin Hall effect was discovered theoretically proposed in 1969 by Diakonov and Perel. And it was only experimentally realized in the year 2004 because it is a very difficult experiment. It took almost 35 years to realize this thing experimentally. So what is spin Hall effect? Suppose you take a bulk piece of metal, for example, platinum, and pass current through it. Then you can create spin accumulation on the surface. And during this process, you will create a spin current, which will be mutually orthogonal to the spin current direction and spin polarization direction, and whose magnitude will be given by this expression over here, where theta is called the spin Hall angle. And the reverse process is also true. You can inject spin current into a piece of aluminum, and you can create a charge current, which will be mutually orthogonal to the spin current direction and spin polarization direction, whose magnitude will be given by this expression over here. Here you can see that there are two spin Hall angles. One you can determine from direct spin Hall effect, and other you can determine from the inverse spin Hall effect. Usually, due to the Onsugar reciprocity, they have this equal magnitude. These two effects are actually the most important effects in spintronics because spin Hall effect gives opportunity to create spin current without any magnetic materials, and inverse spin Hall effect gives opportunity to detect spin current. So the way to detect is you inject spin current into platinum, and and it will produce a charge current. Now, if you put a voltmeter, then you can detect your spin current. So there is also another effect that is called the Raspa effect. People use to produce spin current. So when at the surface of interface of materials, the inversion symmetry is broken. So whenever electron is moving close to the surface and interface, they will experience electric field that is perpendicular to the surface. So in the rest frame of the electrons, it translates into a magnetic field, so which couples to the spin of the electron. So that way, so if you see the Hamiltonian of a two-dimensional electron gas without any spin orbit coupling, you will have this kind of Hamiltonian. We have a parabolic dispersion or spin degenerate dispersion like this one. But due to this Raspa spin orbit coupling term, you will have a momentum dependent spin splitting. Your deep spin degenerate bands will split like this over here, this picture over here. Now, if you make a Fermi, at the Fermi level, you look into the Fermi contours, then you will see that there are two Fermi contours, and the spin in these contours are locked and in a helical structure. And in the year 1990, Edelstein realized that this kind of spin momentum locking can be used for spin charge conversion. And so, but it was only realized experimentally in the year 2013 in the Albert Ford group. They could show that in the bismuth-silver Raspa interface, one can in fact convert spin current to the charge current. So that's why it is called now Raspa-Edelstein effect. So now let me show how you can create spin current to the charge current. So as I said, we have two Fermi contours in a Raspa interface. So now if you pass a charge current, suppose along the negative x direction over here, then the Fermi contours will shift like this over here, and this will produce a spin accumulation, net spin accumulation along the y direction. And if you now connect a metal close to this interface, then the spin current will be injected towards you perpendicular to the surface, and you will create a 3D spin current. And you can now define a quantity called Q, which can define as like the spin charge conversion efficiency. And you can do a little bit of mathematics, and you can show that this Q is related to Raspa parameter and the Fermi velocity and the time constant, which is the spin transmission time across this interface. Now the reverse process, now if you can do a little bit of dimensional analysis over here, you can see that this is a 3D spin current, which is the dimension of ampere per meter square, and this is a 2D charge current, which is a dimension of ampere per meter. So the Q has a dimension of 1/meter. So now the reverse process is also true, in which you can, if you inject a spin current with spin polarization along a y direction, then the Fermi contours will shift like this. The inner contour will shift to the right, and the outer contour will shift to the inner contour will shift to the left, and outer contour will shift to the right. And this will create a 2D charge current, and whose magnitude will be given by this expression over here, where lambda is called the Raspa-Edelstein length. So you can do a little bit of math, and you can show that this Raspa-Edelstein length is related to Raspa parameter and one time constant, which is the relaxation time of out of equilibrium spin distribution. So here also you can do a dimensional analysis. You can see that the Raspa-Edelstein length has a unit of length of meter. So let me summarize some of these, tabulate some of the spin charge conversion efficiency in the two methods. This table summarizes the spin Hall angle of typical heavy metals, present tantalum, platinum, and so on. And this table summarizes most famous Raspa-Edelstein length of most famous Raspa interfaces. And you can see that the Raspa-Edelstein length has a unit of length. So in order to make a comparison between these two, you must have to divide by some kind of length scale in case of Raspa-Edelstein length. So if you assume the interfacial thickness is around 0.4 nanometer in the case of silver bismuth interface, then you can calculate equivalent spin Hall angle to be around 1.5, which is very, very large in compared to any heavy metal we know so far. So that's why Raspa-Edelstein effect is much more efficient for spin charge conversion compared to spin Hall effect. So that's why people are looking for many different kind of Raspa interfaces to study. So in fact, in our group, we have discovered this new Raspa interface, bismuth oxide metal interface, and we have determined the Raspa-Edelstein length with different kind of metals as listed over here. So today I will talk more detail about this kind of interface, how you can convert spin charge using this kind of interface. So let me explain the spin absorption method, how you use this method to study spin charge conversion. So this method involves two steps. In the first step, you demonstrate spin absorption. In the second step, you measure the spin Hall effect. So in the first step, to demonstrate spin absorption, you measure the spin signal, which looks something like this one over here. Now, if you put a spin Hall material in the middle, some of the spin current will be absorbed by the spin Hall material. So if you measure the spin signal again, then you will see that spin signal is reduced. And now if you can calculate the ratio between the two spin signals, then you can calculate the spin resistance of your spin Hall material. And if you know the resistivity of spin Hall material already, then you can calculate the spin diffusion length of your spin Hall material. So now after you have demonstrated the spin absorption, the next thing to do is that if you put a voltmeter, then obviously because some spin current got absorbed by the spin Hall material, it will produce a voltage due to the spin Hall effect, due to the inverse spin Hall effect. So, but since we know that spin current and charge current and spin polarization directions are mutually orthogonal to each other, you will not detect voltage in all conditions. You will detect a voltage only when the spin polarization of the spin current is pointed along the x direction, as shown by this yellow arrow over here. And you can control the spin polarization direction by controlling the magnetization direction of this injector paramagnetic electrode. So suppose you apply large magnetic field along this x direction, you saturate the magnetization along this x direction, and you measure the voltage, then you will get a finite inverse spin Hall resistance over here. And then now if you reduce the voltage to 0, then what will happen is that at 0 magnetic field, this is a ferromagnetic nanowire, so magnetization would like to align along this y direction over here. So in this configuration, you will detect a 0 voltage because this mutual orthogonal condition is not satisfied. So you will voltage will reduce to 0. Since and the same thing will happen if you go to the negative side. And now the difference between these two resistance is called inverse spin Hall signal. If you know this inverse spin Hall signal, you can calculate spin Hall angle using this expression over here. And this measurement, the bottom panel over here, shows the AMR measurement of this one of the ferromagnetic permalloy, which we use to just to cross check our switching fields corresponds to our inverse spin Hall resistance values. So in the same device also you can measure direct spin Hall effect. So in this case, what you have to do is that you have to pass charge current in the spin Hall material, and you create a spin accumulation, and which you can detect non-locally using putting a voltmeter between this ferromagnet and the copper. So in this case also you can get a signal or something like this one, and you can measure direct spin Hall effect. Usually what we see that due to the Oscar reciprocity, the spin Hall angle measured in both methods are equal to each other. So let me give one example how you can use this method to study spin charge conversion and Raspberry dilation effect in bismuth oxide and copper interface. So there is also another motivation for this kind of experiment. There is a fundamental problem in the understanding of Raspberry dilation effect. One of the major problems is that in the spin Hall effect, we convert charge current to spin current and spin current to charge current, and you get these two spin Hall angles. And spin Hall angles are dimensionless. So it is not very difficult to assume that the spin charge conversion will be the spin Hall angle determined by direct spin Hall effect and inverse spin Hall effect will be equal. But if you see the same experiment in Raspberry dilation effect, and the Raspberry dilation coefficient Q has a dimension of 1 over length, and the lambda has a dimension of length. Obviously, these quantities are not the same. So the question comes into mind: is the Raspberry dilation effect, the Oscar reciprocity relation, is valid or not? So this thing has been puzzling to the scientists for a long time. So because there is no single experimental technique exists where you can measure both the things in the same device. But in our non-local measurement methods, you can measure both the things in the same device, and then you can cross-check these things. And let me show how you can do that actually. So to that, I made two kind of devices. This is a one simple non-local spin half device, and other one I made another device in which there in the middle I put a bismuth oxide copper bilayer in the middle over here, and this device was made in 4 different steps of electron beam lithography, and this device was fabricated by me. So, so then after making the device, then you have to measure this red curve over here shows the spin signal of a simple non-local spin half device. And now this blue one shows a device in which there is a bismuth oxide copper in the middle. You can see that the spin signal is reduced because some of the spin current is absorbed by this bilayer. So now we also can measure this spin absorption at all temperatures, not only at this measurement of 10 Kelvin. We found that the spin signal is absorbed at all temperatures. Now, if you can measure the ratio between these two signals, you can calculate how much spin current is absorbed by this bilayer, and this number will be useful to calculate the spin Hall angle. So after you know this things, since we know that some of the spin current is absorbed by this bilayer, now if you put a voltmeter, you should be able to detect some voltage due to the inverse Raspberry dilation effect. So that you can see this blue curve over here shows the spin signal due to the inverse Raspberry dilation effect, similar to the one that I explained earlier. And now I can calculate the inverse Raspberry dilation length using this formula over here. You know this one from this experiment, and the ratio between IC and IS you know from the previous experiment. And from this experiment, I calculated the Raspberry dilation length to be 0.6 nanometer for bismuth oxide and copper bilayer. And in the same experiment also, you can do the direct Rust violation effect. In this case, you pass current in this vial here and create spin accumulation and detect it non-locally. And in this case, you will get this green curve over here. And you can clearly see that this magnitude of the signal due to the inverse Rust violation effect is similar to exactly the same as the signal due to the direct Rust violation effect. And we also measure this signals at all different temperatures, starting from 10 Kelvin to room temperature. We found that the signal due to Rust violation effect and signal due to inverse Rust violation effect, they have the equal magnitude. Now this demonstrated directly experimentally that Onsko's reciprocity is actually not violated, it's valid in this case also. So in order to confirm this thing, we also made many multiple reproducibility checks in which we fabricated a device in which we vary the thickness of the copper from 12.9 nanometers up to 23.1 nanometers. In all the devices, we found the spins, the signal of due to Rust violation effect and inverse Rust violation effect, they have the equal magnitude. Also, we calculated the Rust violation length and the Q, and we found that they doesn't depend on the thickness of the copper. This confirms that the spin charge conversion is not a bulk effect; it's most like an interface effect. So the main takeaway from this slide, this study is that Onsko's reciprocity is valid in case of Rust violation effect, similar to the spin Hall effect. Next, I will come to another next example in which I will show spin Hall effect in manganese 13. So before that, let me talk a little bit about manganese 13. Manganese 13 has a hexagonal structure in which there are Kagome planes stacked along the c-axis, like shown in this picture over here. Now, if you look into one of these Kagome planes, it will look something like this over here, and which contains 3 manganese atoms and 1 tin atom over here. And the spin of the 3 manganese atoms are at 120 degrees with respect to each other. So this kind of spin structure is called inverse triangular spin structure. And this is a non-collinear antiferromagnet. So ideally one would expect that the total spin of this antiferromagnet will be 0, but we found that it has a finite magnetization moment, very, very tiny 0.002 Bohr magneton per manganese atom. So this manganese 13 was discovered in Chaturun Akash's group where I was working. So what we found was that this is a antiferromagnet. It's a very, very tiny magnetic moment, but it shows a very large anomalous Hall effect, large anomalous Nernst effect, and large magnet optical carrier effect. So this was very puzzling to us. So in order to understand this thing further, we also did a angle digital photoemission spectroscopy experiments. And what we found was that in the band structure, it contains these Weil points, and these Weil points have a large Berry curvature. And this Berry curvature can explain all these large transverse transport effects that we observe in our experiments. And since we know that large Berry curvature can also produce a large spin Hall effect, and that was my main motivation to study spin Hall effect in this material, to check does the manganese 13 produce also a large spin Hall effect. So to do that thing, I fabricated this non-local spin valve device kind of thing over here. So in this case, you can see this is a non-local spin valve device, except there is in the middle, that this purple line over here is a manganese 13 nanowire. The width is 200 nanometers and the length is 11 micrometers. So the most difficult part of this device fabrication is that it is very difficult to confirm this nanowire is manganese 13. So to confirm this thing, we just make a hall bar just next to the device. Because people who already fabricated manganese 13 already know it's very difficult to make a thin film. And if you want to make a nanowire, it is even much more difficult. Because most of the nanowire, even if you make a completely stoichiometric nanowire, it will oxidize very, very quickly. So to optimize this device, it took almost 1 year. But at the end, we could fabricate very good quality manganese 13 polycrystalline nanowires. And this is the temperature dependent resistivity of nanowire, in which we deposit nanowire at room temperature and anneal up to 500 degrees centigrade to crystallize. And also, if you measure the Hall bar just next to this device, you could see the anomalous Hall effect. And this anomalous Hall effect disappears at below 150 Kelvin. That confirms that this nanowire is actually manganese 13 and not something else. So after that, we follow the same spin resolution method. So we make one simple non-local spin valve device and measure the spin signal, which looks something like this. And now if you put the manganese 13 in the middle and measure spin signal, you can see the spin signal is reduced, and this measurement is done at 10 Kelvin. But if you do the same measurement at 10 room temperature, you can still see the spin signal is reduced. And from this reduction of the spin signal, you can calculate the spin resistance, and from this you can calculate the spin diffusion length of manganese 13, which I found to be very small, around 0.75 nanometers. So after that, then I did the inverse spin Hall effect experiment, in which you inject a spin current, we suppose spin polarization along this direction by applying magnetic field along this direction. And then you get a finite resistance over here, and then you reverse the magnetic field, then you reverse the spin polarization direction of the spin current, then you will get another resistance, and by measuring the difference between these two resistance, you can calculate the spin Hall angle using this expression over here. And from this experiments, I found the spin Hall angle of manganese 13 is 5%, and which is very close to the spin Hall angle determined for platinum using the same experimental method. And also the spin Hall conductivity was found to be 46 ohm centimeter, which is very close to theoretically predicted value calculated using Berry curvature in the band structures. So this confirms that although we had a very polycrystalline sample, not very good quality manganese 13, still you can get a very large spin Hall conductivity and comparable to theoretical predictions. So the spin Hall conductivity in this material is mostly intrinsic dominated. So after this thing, we also did spin Hall experiment in very high quality manganese 13 single crystals, and there we found a very completely new kind of spin Hall effect. We call it magnetic spin Hall effect, and this was published in Nature, and you can see this paper for further details. So I would like to conclude the presentation now. So I basically saw two different kind of spin charge conversion effects, and I saw how we can use non-local spin charge device to study this thing. The first I showed how you can use non-local spin charge devices and spinization method to study spin Raspberry dilation effect and inverse Raspberry dilation effect. And I saw so that Oscar reciprocity is valid in Raspberry dilation effect. And the second, I saw the non-local spin Hall device can be used to study spin charge conversion in Wilson metals, for example, manganese 13. And I found a very large spin Hall conductivity comparable to theoretically predicted values. And before I conclude, I would like to advertise my group. So I have started a new group in IIT Madras, and my group name is SPINTRONICS Lab. And we are looking for postdocs students. And if you are interested, please apply for this SCRB National Postdoc Fellowship Program, and we will be happy to host you. And thank you very much, everyone. And I'd like to thank all the collaborators and lab colleagues for their contribution to this work.
So thank you, Professor Muduli, for your nice talk. So now we can open the floor for any questions from the audience. So we just unmute and ask.
Hello.
Hello, who's there?
Hello. I'm Shomaru. Am I audible?
Yeah. You can ask.
Yeah, I have one very basic questions. That in case of spin Hall effect based like platinum or tungsten, the spin Hall angle is depend on the SOC strength, spin orbit coupling strength. So for your that Raspberry Dilston interface, what is the parameter of the material or property of the material is crucial?
The parameter crucial is the Raspberry parameter, this alpha, so which is kind of quantifies the splitting parameters. This alpha is the most critical parameter for spin charge conversion.
No,
because you need a material with a very large. It's a material property. This is interface property. So depending on different material, different interface, you will have different alpha.
Okay, but
so because this
in our
for example, this
or
yeah, so you can see this different interface have different Raspberry dilation length because they have different Raspberry parameters. So depending if you have a very large Raspberry parameters, so you can have a very large spin charge conversion. For example, this interface has a much larger bismuth silver has a very large Raspberry parameter compared to iron germanium interface. So that's why we have a large Raspberry dilation length in bismuth silver interface. So it is a material interface dependent parameter. So depending on the quality, it depends on the interface. For example, bismuth oxide silver might have a smaller Raspberry parameter compared to bismuth copper interface or bismuth aluminum interface, for example, here.
So as it is a interface dependent parameter, so the interface quality has any effect on this parameter? I mean, a good quality interface or a bad quality interface, like in terms of if you say interface roughness, maybe. So does it vary with interface roughness kind of stuff?
In that way, interface roughness may not be that may contribute something extrinsically, but if you consider ideal interface, basically the Raspberry effect is like the electrons are moving close to the interface, and at the interface actually they're experiencing a electric field which is perpendicular to the surface. and that magnitude depends on what is the potential barrier at that interface. So, and that depends on the work function of these two materials and so on. So the roughness will probably provide something, some other extrinsic mechanism which will probably reduce your spin charge conversion efficiency. But experimentally, you need a very good quality closely in the interface to maximize your spin charge conversion efficiency, because the roughness will provide some spin scattering sources which we can reduce your spin charge conversion efficiency.
Thank you. Thank you.
Hello, sir.
Yeah.
Hello.
Yeah.
Hello, sir.
Hello.
Yes, sir. So I want to know, sir, that means a spin resistivity and a spin mobility. So on which parameter this spin resistivity and spin mobility will depends?
Okay, let me go to next slide. Yeah. So here actually you can, the spin resistance is defined like this one here, which depends on the spin diffusion length and the resistivity of the material and the spin polarization of the material. And suppose you have a nanowire, it depends on the area cross section of your nanowire. For example, if you have non-magnetic material, for example copper, the spin polarization is 0 because it's not magnetic. So it will depend only on the resistivity and the area cross section and your spin diffusion length. But if you have magnetic material, then you have finite spin polarization, and so you have to consider all these concepts. And usually, for example, in a copper, the spin diffusion length is very large. So that's why you have a very large spin resistance. And for example, if a permalloy, the spin resistance is lower because the spin diffusion length is very, very small, around 5 nanometers. So it is very counterintuitive. For example, permalloy electrically has a very large resistivity but compared to copper. But in terms of spin resistance, copper has a more higher spin resistance compared to permalloy. So the spin resistance depends quite a, you have to consider the spin diffusion length, not only the resistivity.
Sir, actually, that means resistivity of a material or spin resistivity of a material will same?
They are not same. They are very different actually. That's what I am saying. So if the resistivity can be of a material can be larger, but if the spin diffusion length is smaller, you can have a smaller spin resistance. For example, in permalloy, iron nickel alloy, the spin diffusion length is very, very small compared to copper.
Actually, isolated.
So the permalloy has a very low spin resistance.
Actually, I want only about the resistivity, spin resistivity of a material, not resistance.
Yeah, the spin resistivity, as such, there is no special definition on resistivity. But if you remove this area, maybe you can call this something like spin resistivity. But it depends on the product of the spin diffusion length and the electrical resistivity. So it doesn't only depends on the resistivity. It also, one has to know the spin diffusion length inside this material.
Okay. In general, in aspects of resistivity depend upon the relaxation times, mass, effective mass. So like that, like why I want to know that.
Yeah, so like that, actually, it depends on the spin relaxation time, and because it has spin, the lambda s depends on the spin relaxation time and diffusion constant, and the rho depends on the relaxation electrical transport relaxation time. So you can say that it depends on two relaxation time. One, your relaxation time of charge scattering events, other is the spin relaxation time. So more only electrical resistivity depends only on your scattering time tau, the momentum scattering time.
Okay, sir. Answer.
It's kind of a product thing. So.
Can I ask one more question?
Due to the constraint of time, I think we would like to move to the next speaker. I'm sorry. So if you have anyone else has any other question, I see Sajid.
I have just one basic question.
Okay,
Thank you first. Thank you, Dr. Muduli, for very excellent work and excellent talk. So one question regarding the non-collinear antiferromagnet. You know, this non-collinear antiferromagnet had this directional dependence. So anisotropic spin Hall angle, especially for example, magnets 3 platinum case. So if you if your orientation of your crystal is different, if you inject your current direction, like if you inject your current in different direction, you have different spin charge conversion, you have different spin Hall angle. So do you think like in your crystal it could it could behave like this, or it doesn't have any direction dependent
Yeah,
talks
actually,
in your material?
yeah, this is a good question. Actually, in our experiment, we could see some evidence, experimental evidence. For example, you can see that this the experimental data is not symmetric around origin, and
Right.
so what happens? It is zero magnetic field. So at zero magnetic field, what is happening is that if you at zero magnetic field, the magnetization spin polarization direction is along this long axis. So at zero magnetic field, you should not get any inverse spinel signal at all. According to this, if you assume that this relation is valid, spin current, spin polarization direction, and charge current has to be mutually orthogonal. But this doesn't happen here. This is because this material supports some spin accumulation in other directions. So one expects some spin accumulation which is perpendicular to the surface. So there is some other mechanism present, and we call it magnetic spin Hall effect. So that is why there is a signal is shifted. So it is possible to see
Yeah,
this kind of effects in this data also.
that's why I asked the question, because the spin Hall angle even is larger in quite large in one direction, and is very small in your, and in your case you have just 5%. So I was wondering if you have maybe more than 10% or maybe 20% in one direction. So that would be an interesting thing
Yeah,
to know.
it's a good question. Actually, the actual spin Hall, the total spin Hall angle will depend on the magnetic spin Hall angle plus your normal ordinary spin charge conversion. So if sometimes your magnetic spin Hall effect will be dominating, then you can have a very large spin Hall angle in certain orientation direction. Yeah.
Thank you.
So I think in the nature paper we have done angle dependent study. You can see in this paper there is angle dependent study where we have seen that when it is actually 60 degrees with respect to your applied direction, the spin Hall angle is maximized. There is an angle dependent study in this paper.
Yeah, that's what I was asking. Okay, thank you. Yes, I will see that.
Okay, thank you, Professor Muduli, for your nice talk and for answering all the questions. So now we will move on to the next speaker, Professor Braj Bhushan Singh. So Professor Braj Bhushan Singh, is he there?
Yeah.